So this is the 9th section of the differentiation chapter, and this is all about identifying which parts of a graph are concave or convex, or maybe it may be neither of the two, or it may be changing between the two. So the way that we decide if a function is concave or convex is we need the second derivative. So the second derivative is either f double dash of x or d squared y over dx squared. So it can be written either way. And once we've calculated that, that will tell us if a function is convex or concave. And what we're looking for is what's the value of this second derivative for particular values of x. Now, if the function or the second derivative, if that's less than or equal to 0, or it could actually be that it's less than 0, that means that the function for those particular values of x is concave. If the second derivative is greater than or equal to 0, or it could be that it's greater than 0, the function is convex. So that's what we need to know. Okay, so there's some examples down here of some functions. Now, if we worked out the second derivative, so there we've got y equals 5x minus x squared. So dy dx, if we differentiated it once, we would have 5 minus 2x. If we differentiated it a second time, we would get negative 2. Now, it's always going to be negative, isn't it? So we could say something like, so the second derivative is always less than 0, or less than or equal to 0, which means that, going back to our definition here, that this function is concave for all values of x. Yeah, so that just means all values of x. Because it doesn't matter what x is, you're always going to get negative 2 as the second derivative. So wherever you go on this graph, it's always concave. The second one, which is y equals e to the x. Now, if we differentiate that, this is an easy one to differentiate. It's just e to the x. Second derivative, d squared y over dx squared, is also e to the x. Now, what do we know about e to the x? E to the x is always greater than 0. So if it's always greater than 0, that means that this function here is convex. Again, for any value of x, because it doesn't matter whatever value of x you use, e to the x is always going to be greater than 0. So this one is convex, and again for all values of r, or all values of x. R just means real numbers, that funny looking R there, real numbers. Now if we look at the last function at the end, if we differentiate it once, so dx dy, or dy dx, is 3x squared minus 12x minus 9. If we differentiate a second time, that's going to be 6x minus 12. Now this is different to the previous ones in that sometimes it's positive and sometimes it's negative. It all depends. Now we can work it out actually by, if we solve that equal to 0, So So if we did 6x minus 12 equals 0, we would have 6x equals 12, which would give us x equals 2. Now this gives us the point at which 6x minus 12 changes from positive to negative. Now if I put a number smaller than 2 into 6x minus 12, so if I put like 1, 0, negative 1 into that, I'm always going to get a number which is negative. So for example, 6 times 1 minus 12 minus 6, 6 times 0 minus 12 is negative 12. So when x is less than 2, now they've done less than or equal to 2, so they're sort of interchangeable. So here you could have when x is less than 2, that means that the second derivative is going to be negative, and if the second derivative is negative, we have a concave function. When x is greater than 2, 6x minus 12 is going to be positive. So example, if x is 3, I get 18 minus 12, which is 6. 6 times. If x is 4, I get 24 minus 12, which is 12. So if x is greater than 2 here, that means that the second derivative is going to be positive, and if the second derivative is positive, then I'm going to have a convex function. Now again, this could be x is greater than 2. It doesn't have to be greater than or equal to. So on this one here, we need to find the interval on which the function is concave. Now what that means is that we're looking for when the second derivative is less than 0. So we'll just write that down. So concave basically means, okay, when is the second derivative of this function less than or equal to 0. So let's start by finding the second derivative. So the first derivative, f dash of x, so we're going to use the same notation. That's going to be 3x squared plus 4. Sorry, that's a squared there. Let's tidy that up. So the second derivative is going to be 6x. So we want to find out when that is less than or equal to 0, and that's an easy one. 6x is going to be less than or equal to 0, and actually you can just solve this by dividing by 6 when x is less than or equal to 0. So the interval on which that function is concave. Now there's a few ways that we can write this down. So we could write it like that. X is less than 0, less than or equal to 0, or we could write it down like as a set. So basically it's from negative infinity, so it's the set of numbers from negative infinity to 0. Yeah. So there's different ways in which we could express our answer, but that's pretty much the answer. That's the interval for which the second derivative is less than 0. Less than 0 means concave. This one, show that the function is convex for all real values. So it's sort of given us something here. We're expecting that when we work out the second derivative, that's always going to be greater than 0 for all values of x, but we need to show that. So the first derivative, that's going to be 2e to the 2x plus 2x. The second derivative is going to be 4e to 2x plus 2. Now this bit here is always going to be greater than 0. Anything with e with a positive power or with any power is always going to be greater than 0. So that first bit is greater than 0 always, and then you're adding 2 to that, so you're always going to end up with something that's greater than 2. So basically you're going to end up with something that's always positive. So if you end up with something that's always positive, that means that this function f of x, therefore f of x is concave for all values of x, all real numbers. Now sometimes we have something which is called a point of inflection, and a point of inflection is defined as the space between the part of the graph which is concave and convex. So you can see that this part of the graph up here is the concave part. This part of the graph is convex. So we'd really need the function to help us work that out. Even without knowing what the function is, there are a couple of other ways of identifying when a graph is convex and concave. So the first one involves using what we call line segments. Now what I mean by line segments are going to be lines which I draw which connect one part of a graph to another. Now if I picked the part of the graph which was concave and I drew lines which joined one part of the graph to another, so from anywhere to anywhere in this bit that's labelled red, so like that, like this. So all I'm doing is just joining one part of the graph to another where the graph is concave. Do you notice that all of those green lines that I've drawn are below the graph? So with side line segments joining one part of the graph to another, if it's concave, then none of those line segments will go above the graph. So let's think of concave. The line segments, they're always going to be always below the graph. That's another definition. Whereas in the convex bit, let's do the same thing again. Let's join any two parts of this red bit where we know that it's convex. Do you notice that all of these lines are above the graph? So we've got like the opposite definition. Where a graph is convex, these line segments are always above the graph. So that's another way of thinking of it. Another way is to do with tangents. So another way is tangents. So let's take out all of these line segments here and here, and what we're going to do is we're going to replace and draw tangents instead. So if I were to draw tangents in the part of the graph which is concave, so any tangent anywhere here, and I'm going to do the same here. I'm just going to draw tangents wherever I feel like this. Yeah. Now what do you notice about the tangents? Well, in the concave part of the graph, all the tangents are above, and in the convex part of the graph, all the tangents are below. So this is another way of identifying where a graph is convex and concave. So we'll just write that down. Concave with tangents. Those tangents are always going to be always above the graph, so the opposite to the line segments, always above the graph, and convex is going to be the opposite to the line segments again. The tangents are always below the graph, always below the graph, which means that when a graph isn't convex or concave, we're going to have an area where either these line segments change from being above the graph to below, or vice versa, and the same with the tangents. We're going to have a part of the graph, and it's this bit in the middle here where the tangents don't seem to be either above or below. They almost like lie on the graph like that. So this is going to be where the second derivative is neither greater than 0 or less than 0. It's going to be, and I'll highlight it up here, where the second derivative equals 0. And that's where we get this point of inflection, which is this bit here, where the graph is changing from being convex to concave, or concave to convex, and then between the two we have a point of inflection. So if we were to write that down, so a graph may start off being concave, you get a point of inflection, and then it becomes convex, or we could have the opposite. It starts convex, we get a point of inflection, and then it becomes concave. The curve C has the equation y equals x cubed minus 2x squared minus 4x plus 5. Show that C is concave on this interval between those values, and convex in this interval. Okay. So the first thing we need to do is to differentiate twice, because that's going to help us work out when this curve is convex and concave. So if you differentiate once, we'll get 3x squared minus 4x minus 4. If we differentiate a second time, we will get 6x minus 4. Now there's lots of different ways we can do this, but what we do know is that when a function is concave, the second derivative is less than 0, or less than or equal to 0. You could have either one. When a function is convex, the second derivative is greater than or equal to 0. So here we could have just this. Yeah, so either one of those is fine. So we want to find out when 6x minus 4 is less than 0 and when it's greater than 0. So one way of doing it is actually just to sketch the graph of 6y plus 4, 6x plus 4. So you've got x there, you've got y there. So what this is a straight line graph with a gradient of 6 crossing at negative 4 here. Yeah, just using y equals mx plus c. Now we can work out this point here where it crosses the axis. So that point there is where 6x minus 4 equals 0. So 6x equals 4, x equals 4 over 6, which is 2/3. Right, so that point there where it crosses the axis is 2/3. So let's put that on. 2/3. Right, so this is basically this graph, and we want to find out or show, first of all, in the interval from -2 to 0. So -2 to 0 is going to be like from here. This is not to scale. -2 to 0. Okay, is that graph below the axis? Yes, it is. I can see it down here. Yeah, so I can at x equals minus 2. Second derivative, yeah, that would be equal to negative 12 minus 4, negative 16. And at the other end of the interval, x equals 0. The second derivative is going to be negative 4. Okay, and then since it's linear, since this is linear, it's linear, see that is always going to be less than 0, so that shows that it's concave. Okay, let's have a look at the graph between the other interval, which is 1 and 3. So 1 is going to be here, 3 is going to be here, so I can see, yes, in that interval it's definitely positive, it's above the axis. So I can do the same thing again. I can say, well, at x equals 1, the second derivative is going to be 6 times 1 minus 4, which is 2. And at x equals 3, the other end of the interval, the second derivative is going to be 6 times 3, 18 minus 4, which is 14. I'll say the same thing again. Since second derivative is linear, the second derivative is greater than 0. I suppose I should put in the interval as well. So I should put here that this is between minus 2 and 0. And here I should also put that this is between 1 and 3. So that leads us to believe that this is convex. Okay, so we've done that. Part B, when it says find the points of inflection. Now the points of inflection occur when a graph goes from convex to concave. So it's going from convex to concave, or the other way around. So it goes from that to that, and then in between there we will find the second derivative equal to 0, and when we find that point not of 0, second derivative of x equals 0, and then if we find the value of x, that gives us the x coordinate of the point of inflection, and then we can use that to find a y coordinate. So we know that this second derivative goes from concave to convex, so we're trying to find a point where the second derivative equals 0. So I don't need to show that it's going concave to convex. So equals that, and we want to find out when that equals 0, and that equals 0 when x is 2/3. That's easily enough to do. To find the y coordinate, I put 2/3 into the original equation, so it's going to be 2/3 cubed minus 2 times 2/3 squared minus 4 times 2/3 plus 5. Let's put that in on the calculator and see what we get. Now to speed things up again, I'm going to type, or speed things up, I'm going to type in 2/3, press equal, so that's stored. So all I need to do is answer cubed minus 2 times answer squared minus 4 times answer plus 5. It's quicker than typing in 2/3 lots of times. And I get 47 over 27. So 47 over 27. So the coordinates of the point of inflection is going to be 2/3, because that was the x, 47 over 27. And I'd keep these like that. I'd keep them exact. I wouldn't start messing around and changing these into decimals.